In the present video, I'm going to show you some exercises presented in the book by Logarithmic, where he presents spirals. The idea here being that you can develop a spiral as an expanding curve that, in a sense, is a fractal, but it's a regular fractal, or let me put it, is a regular curve that expands the plane. And so we're going to present some examples of spirals in this case, beginning with a program that Logarithmic calls UNWIND. It's on page 58, figure 4.5. I have a small program called mCircle that will draw a circular shape, and this is the curve called, or the program called UNWIND, that produces as a result the circle of radius A and a collection of coordinates to produce the unwinding curve. The result is a graphic like this. The circle, of course, is constant, and then you have this spiral that grows with the angle, and then you get lines that are tangent to the circle and sort of like go out to meet the spiral. You could find these shapes in nature, in snails or other type of marine life, and so it is a common shape found in life. And we have two parameters to deal with. One is the radius of the circle, that's the center of the curve, and delta n is an increment in the number of these lines that join the circle with the unwinding spiral. And so the value of 5, I started with value of 5 here. If I put 10, then the distance, the delta n is actually the difference in the angle. You get less lines. So the smaller that this second argument is, the more lines in your spiral connecting the circle you're going to find. And so let me try 2 here, and you're going to see more lines, with 1 even more lines, because it's just the increment in the spacing. And if you go to smaller values like 0.5 and 0.25, then the figure becomes more and more full with lines. But actually, apparently for values smaller than 1, it won't change. So this is the first example of a spiral presented in the textbook by Logarithmic. We're going to look at Archimedes spiral. And it is presented here in this program using parametric equations. The radial distance grows linearly, and the x and y position it would be sort of the corresponding coordinates of a circle, but with r increasing, then the circle is never completed. Instead, you start getting a curve such that the distance between two branches of the curve is the same, but it's spiraling out, and this is the Archimedes spiral, which is not a fractal in the regular sense, but it is a curve that tends to fill the plane, which is a characteristic of fractals. And so this is the case for relatively small numbers here. Actually, the Archimedes with 8 took a long time to produce, and so I took a picture of it to put it in here, so you don't have to be waiting. But this is our Archimedes for 4. This one was generated relatively quickly. Let me see if we can do it with 6. It's going to take some time, and so I'm gonna pause it and show you. No, there it is. It didn't take that long. Anyway, so that's the idea behind the Archimedes spiral. That's the second case. The third case is the logarithmic spiral. And again, the x and y coordinates are calculated like if you were calculating the coordinates of a circle, but the radial distance is exponentially growing with the parameter t. A and b are a couple of parameters. A is the the amplitude of this exponential growth function, and bt is another argument for the argument of the exponential function. And here we have a values of t going from 0 to 42 in increments of 0.2. And so if I were to figure out what is the length of that vector, you find that there are 211 points. And so it takes a little bit to produce all those points. The original version in the textbook by Lewis, page 63, figure 411, uses 0.1 in here, and so it takes a while to produce the spiral. The logarithmic spiral, of course, is a spiral that's winding, and at the same time the distance between the branches is growing with the parameter t. To finish up this presentation, we're going to look at this spherical spider, and I think, I mean, this is just not spider, spiral, sorry. It's a projection of a three-dimensional, as you can see there's an x, y, z, using these UMV points that are the ones that get stacked, to produce the spherical shape. And so you can see that like a sphere that is growing towards the center of a sphere and then decreasing towards the south pole. And that's the basic idea behind this particular spiral. Nothing complicated, just another example of a spiral. So spirals may not be fractal, but they have an interesting characteristics, and that was the idea behind this presentation.